The British Army reviewed flamethrowers. Early files referenced German models. War planners requested domestic designs. Industry received urgent development tasks. Initial requirements were concise: infantry support weapon, portable by one man, capable of short intense bursts, capable of clearing fixed positions. Weight limits were specified. Range figures were aspirational. Service life was secondary. Crew safety was assumed acceptable. Design responsibility moved between departments. The Directorate of Artillery commented. The Ministry of Supply coordinated. Inspection branches monitored finished units. Engineers started with basic principles. Pressurised fuel reservoir on the back. Propellant cylinder mounted beside tanks. Flexible hose leading to nozzle. Trigger valve at the nozzle. Fuel formulation became central. Straight petrol atomized too quickly. Diesel alone lacked volatility. Thickened blends were investigated. Rubber-based thickeners were trialled. Laboratories mixed multiple blends. Some used aluminium soaps. Some used latex derivatives. Others used proprietary commercial gels. The mixture was called fuel. Its exact recipe varied. Viscosity targets were approximate. Cold weather performance was uncertain. Propellant choice required compromise. Compressed air was available. Compressed nitrogen was safer. Carbon dioxide was considered briefly. Nitrogen cylinders were adopted widely. Working pressures were substantial. Figures approached several dozen atmospheres. Cylinder valves used simple packings. Early packings used natural rubber. Some used leather discs. A few used cork-based washers. Compatibility tests remained limited. Fuel tanks were steel, cylindrical shells with welded ends. Internal baffles were minimal. Corrosion protection was basic paint. Tanks were mounted vertically. Backpack frames used mild steel. Shoulder straps used webbing material. Harness padding was often minimal. The overall silhouette was bulky. Weight in service exceeded requirements. Operators noticed strain during marches. Stability while crawling was poor. The hose was critical. It carried pressurized fuel mixture. Early hose used rubber tubing. Cotton braiding provided external reinforcement. Rubber swelling became evident. Fuel components attacked internal lining. Hoses softened after repeated use. Micro cracks appeared in flexing zones. Couplings joined hose to tank. Threaded unions lacked secondary seals. Flat fiber washers provided sealing. Tightening relied on manual judgment. Repeated assembly damaged threads. Cross-threading occurred under stress. Damaged couplings trapped fuel residues. Cleanliness procedures were inconsistently followed. The nozzle unit combined functions: a small pilot flame igniter, a main discharge valve mechanism, a simple directional tube for projection. Ignition devices varied by batch. Some used pyrotechnic cartridges. Others used electrical spark systems. Matches and lighters appeared during training. Pilot flames sat near the operator. Fuel stream passed directly ahead. Any local leak presented risk. Spray patterns could envelop the harness. Testing occurred on military ranges. Demonstrations emphasized effect on targets. Wooden structures were quickly ignited. Sandbag emplacements were visibly scorched. Reports highlighted target destruction. Less attention covered operator exposure. Range officers stood at distances. Leak patterns were not fully documented. Trial durations were limited. Few continuous discharge cycles conducted. Long-term endurance remained understudied. Rubber aging data was incomplete. Production contracts were signed quickly. Factories modified existing equipment lines. Oxyacetylene parts were reused. Diving apparatus components were adapted. Welding jigs were improvised rapidly. Inspection gauges lagged behind deliveries. Dimensional tolerances drifted between batches. Field units received non-uniform equipment. Instruction manuals followed later. Preliminary pamphlets circulated first. Illustrations showed ideal assembly states. Fault conditions received minimal coverage. Training courses were concise. Instructors were sometimes inexperienced. Practical time with live fuel was limited. Simulated drills used water substitutes. Water drills hid several issues. Water did not attack seals. Water did not soften hose linings. Water leaks evaporated without odor. Fuel behaved differently in practice. It seeped slowly through micro cracks. It collected in harness folds. It coated valve bodies externally. Operators noticed faint odors. Some reported damp straps. Others observed darkened hose surfaces. Formal complaints remained sparse initially. Combat deployment began cautiously. Flamethrower sections supported assault teams. Roles focused on bunker clearance. Psychological expectations overshadowed technical doubts. Field conditions stressed the equipment. Mud contaminated moving components. Dust entered couplings and valves. Temperature swings affected rubber elasticity. Leaking incidents became more frequent. Small weeps appeared at unions. Sweating hoses left thin films. Gloved hands spread contamination unknowingly. Ignition procedures seldom changed. Pilot flames were still lit. Operators advanced with burning igniters. Fuel vapor existed around them. Under certain wind angles, under certain posture combinations, vapor clouds formed near tanks. The pilot flame provided ignition source. Some accidents occurred during rehearsals, others occurred under enemy fire. Patterns shared common elements, leaking fittings behind the nozzle. Witness reports mentioned sudden flashes. They described sheets of flame. Flame travelled back along the hose. Flame reached the fuel pack. Protective clothing offered limited defense. Standard battle dress was flammable. And anti-gas capes provided partial shielding. Face and hands remained vulnerable. After incidents, equipment was inspected. Burn patterns showed rearward ignition. Charred harness edges were visible. Tank exterior paint was blistered. Investigators traced fuel pathways. Residue marks showed leak routes. Drops had run down frames. Straps had carried fuel laterally. Laboratory reconstructions were attempted. Test rigs reproduced joint leakage. Artificial mist clouds were generated. Pilot flames ignited them consistently. Reports identified sealing weaknesses. Recommendations included improved washers. Suggested secondary seals around threads. Proposed double hose clamping points. Implementation took additional time. Existing stocks remained in use. Frontline units improvised modifications. They added rag wrappings around joints. Some units reduced live training. Others restricted flamethrower deployment frequency. Preference shifted toward alternative explosives. Demolition charges seemed more controllable. A cultural perception developed gradually. Operators considered the weapon unreliable. Rumors circulated of spontaneous ignition. Nicknames reflected perceived self-destruction. Bureaucratic language softened descriptions. Documents spoke of operational hazards. They referenced increased maintenance vigilance. They advised careful handling under fire. Formal withdrawal did not occur immediately. Instead, usage became selective. Commanders weighed risk against effect. Many chose conventional firepower instead. Engineering staff pursued incremental changes. They trialed improved hose compounds. They tested synthetic rubber blends. And compatibility improved under laboratory conditions. Valve designs were revised carefully. Spindle packings gained secondary seals. Gland nuts received lock features. Operational settings required measurable torque. Tank connections added recess grooves. These accepted O-ring inserts. O-rings provided elastic sealing. Manufacture demanded tighter machining tolerances. Not all factories retooled quickly. Older patterns stayed in circulation. Frontline depots mixed types. Records rarely tracked exact configurations. Fuel formulations also evolved. Thickening agents changed over time. Mixtures aimed for reduced vapor release. Cold flow properties were adjusted repeatedly. Each adjustment introduced new interactions. Some blends attacked older seals. Others separated during long storage. Phase separation altered flow consistency. And transport arrangements added more variables. Tanks travelled on open lorries. Temperature exposure varied significantly by route. Thermal expansion stressed internal weld seams. Inspection routines struggled to keep pace. Technicians followed checklists under pressure. They prioritized obvious mechanical defects. Minor seepage sometimes passed unrecorded. Field modifications lacked standardization. Some crews taped joints heavily. Others added improvised splash guards. Some shortened hoses to reduce snags. Shortened hoses increased rigidity. Bending radii exceeded design assumptions. Microcracks formed at constrained sections. Pressurization cycles enlarged existing flaws. During assaults, stress increased sharply. Operators crawled under fire, backplates scraped against rubble surfaces. Couplings struck hard obstacles repeatedly. Mechanical shocks disturbed thread seating. Partially loosened unions leaked further. Fuel droplets spread across clothing. Awareness remained low in moments. When discharge began normally, the flame projected toward targets. Observing troops focused on impact. Few watched the operator closely. In accident cases, progression altered. Flame envelope widened unexpectedly backward. Observers saw sudden torso ignition. Equipment silhouette disappeared in bright flare. Medical summaries were understated. They listed burns to operators. They referenced equipment-related causes. They avoided detailed anatomical descriptions. Subsequent memoranda revisited doctrine. They questioned close-range employment. They argued for vehicle-mounted systems. Armor provided separation from fuel. Tracked flamethrowers gained priority gradually. And infantry portable sets lost advocates. Design groups shifted their attention. Resources moved to armoured conversions. Nevertheless, existing stocks lingered. Depot inventories showed residual holdings. Training centres retained demonstration pieces. Manuals remained on official shelves. Later historical reviews examined files. They noted emphasis on effect. They noted underemphasis on survivability. They saw repeated references to haste. Specifications had favoured output metrics. Range figures impressed senior officers. Ignition reliability pleased demonstrators. Crew risk received general statements only. Sealing science advanced slowly then. Polymer understanding was incomplete. Manufacturers relied on practical recipes. Aging behaviour was poorly predicted. Alternative engineering paths were possible. One path required thicker hoses, another required full double containment. Both increased weight significantly overall. Procurement officers resisted extra weight. Infantry planners insisted on mobility. Reduced range was unacceptable supposedly. Additional cylinders were dismissed as cumbersome. Thus compromises stayed embedded. Light enough for assault movement. Powerful enough for short-range devastation. Safe enough in theoretical assessments. Battlefield experience contradicted assessments. Operators saw fuel around them. They smelled vapour under harness. They heard hiss from joints sometimes. Some refused deployment quietly. Some requested reassignment to other tasks. Others carried sets but never fired. Official records rarely captured such choices. The design story shows interaction. Engineering numbers met administrative pressures. Laboratory success met field ignorance. Safety margins met operational improvisation. In strictly technical terms, the British portable flamethrower functioned. It delivered fuel toward designated targets. Measured ranges matched stated requirements. In equally technical terms, its sealing systems remained fragile. Its hose materials degraded systematically. Its ignition system tolerated surrounding vapour. These conditions combined under stress. The weapon could burn its operator, not through intention or doctrine, through cumulative small design choices. In later decades, assessments softened. Documents described a necessary experiment. They framed incidents as learning stages. They highlighted subsequent safety improvements elsewhere, but the core pattern persists. A rushed development left sealing weaknesses. Weaknesses met volatile fuel mixtures. Ignition sources sat inches away for the operators involved. The weapon was not abstract, it was weight on their spine, it was heat against their back. Their experience shaped reputations. Units with options chose otherwise. Flamethrower sets stayed in crates. Other tools went forward instead. The British programme continued officially. It refined valves and seals. It trialled better materials gradually. Yet early impressions remained embedded. Within archives the evidence sits. Test logs document pressures and flows. Accident notes record dates and units. Memoranda summarize technical recommendations. Together they describe a pattern. An infantry weapon meeting specifications. A system that endangered its crew. And a project constrained by urgent necessity. Subsequent technical committees met periodically. They reviewed prior incident summaries. They correlated failure modes with environments. They produced tables of contributing factors. Moisture content appeared repeatedly. Dust contamination appeared alongside moisture. Improvised repairs appeared in annotations. Training shortfalls appeared in narrative remarks. One paper studied joint geometry. It compared parallel and tapered threads. It examined torque versus sealing performance. It recommended controlled tightening procedures. Another paper assessed harness layout. It mapped likely leak trajectories. It plotted fuel runoff paths. It identified fabric accumulation zones. Suggestions included drip shields. Suggestions included absorbent collars. And suggestions included sacrificial outer covers. Most were classed as field expedients. Official drawings changed more slowly. Printing backlogs delayed distribution cycles. Units operated from outdated diagrams. Workshops guessed at correct configurations. Procurement correspondence shows persistent tension. Ordnance branches requested safer assemblies. Financial officers highlighted existing contracts. Production managers resisted mid-run alterations. The weapon remained a compromise item. It satisfied operational demands on paper. It stressed technical staff in practice. It alarmed those required to carry it. Later design notes pursued modularity. They discussed detachable fuel modules. They considered separate propellant units. They examined quick-release harness couplings. Quick-release concepts raised questions. So could packs be jettisoned while burning? Would hoses park cleanly under load? Would residual flames follow escaping vapor? Test footage answered partially. Jettisoned packs sometimes extinguished successfully. Others continued burning on the ground. Some rolled unpredictably on uneven terrain. Safety margins remained conditional. They depended on precise operator movements. They depended on surface character underfoot. They depended on wind and fuel temperature. Archive photographs add further detail. They show patchwork repair patterns. They show mixed generations of fittings. They show crews carrying unfamiliar equipment. Labels on cylinders vary by batch. Some show clear nitrogen markings. Others carry ambiguous contents descriptions. A few lack legible stamping entirely. Ambiguity complicates later reconstruction. An exact propellant used in accidents. Exact fuel blend at given dates. Exact maintenance history of each set. These remain partially unresolved questions. Analysts rely on indirect indicators. They compare scorch patterns between incidents. They triangulate testimony with component samples. The overall engineering picture stabilizes. Pressure systems performed within tolerance. Fuel blends produced required flame adhesion. Sealing interfaces lagged behind both. The history also intersects doctrine. British forces studied urban fighting. They anticipated fortified cellars and strongpoints. They saw flamethrowers as technical answers. Exercises on mock villages occurred. Observers recorded clearance times. They timed bunker neutralization under supervision. They filed graphs demonstrating improved speed. Such data influenced allocation decisions. Senior headquarters prioritized assault battalions. Smaller formations received older sets. Some retained equipment already criticized privately. In theaters with dense vegetation, humidity raised separate difficulties. Hose exteriors remained permanently damp. Mold formed beneath harness padding. Dampness masked fresh fuel seepage. Operators could not distinguish odors. Leak detection became further impaired. Incident likelihood increased correspondingly there. Despite these factors, the project persisted. Replacing a weapon family took years. Cancelling a specification required justification. Admitting unacceptable risk carried institutional weight. Thus, memoranda adopted constrained language. They referred to heightened awareness measures. They mandated enhanced inspection frequencies. They recommended additional commander briefings. None altered the core equation. A man carried fuel and propellant. He stood near an open flame. His survival depended on intact seals. In that sense, assessment simplifies. The British portable flamethrower illustrates boundary conditions. It lies where acceptable risk approaches threshold. It lies where engineering shortcuts become visible. Its record never equals artillery totals. Its incidents sit amid larger casualties. Yet its failures are mechanically specific. They arise from identifiable physical mechanisms for the research staff involved. The files remain a technical resource. They capture real responses under stress. They record how components behave when misused. For those who carried the frames, the weapon became a reputation. It earned a place in informal warnings. And it shaped how volunteers came forward. That combination defines its legacy. A functioning system meeting early papers, a compromised device distrusted by users, a British flamethrower capable of burning crews.